November 24, 1944, in a camouflaged hangar outside Tokyo, a team of Japanese aviation engineers gathered around what remained of a B-29 superfortress that had crash-landed near Yokohama 3 weeks earlier. The aircraft, tail number 42-24620, had been extracted from its impact site with extraordinary care, transported in sections through the night to avoid Allied reconnaissance, and reassembled inside this secure facility. Captain Hiroshi Tanaka, one of Japan's most accomplished radar technicians, stood before the bomber's nose section with a mixture of professional curiosity and barely concealed dread. He had been ordered to examine the aircraft's electronic systems, to understand how American bombers were finding their targets with such uncanny precision through darkness, cloud cover, and the smoke of war. What he would discover over the following weeks would shake his understanding of the technological gulf between Japan and the United States, and introduce him to what he would later describe in his classified report as a machine that sees through the eyes of God himself. The B-29 superfortress represented the apex of American industrial and technological achievement in 1944, a strategic bomber so advanced that its development had cost more than the Manhattan Project, with a pressurized cabin allowing flight at altitudes beyond the reach of most Japanese fighters, defensive armament controlled by a revolutionary computerized fire control system, and a bomb load capacity that dwarfed any previous aircraft. The B-29 was not merely a weapon, but a symbol of American technological supremacy. Yet even among its many revolutionary systems, the AN/APQ-13 radar bombing system stood out as particularly sophisticated, a device that allowed bombardiers to identify and strike targets through complete darkness or total cloud cover, rendering weather and night no longer sanctuaries from aerial attack. Japanese military intelligence had been tracking B-29 raids since the first strikes from Chinese bases in June 1944, and the pattern troubled them deeply. American bombers were hitting targets with a precision that seemed impossible given the conditions. Night raids were achieving accuracy comparable to daylight attacks. Strikes conducted through solid cloud cover were destroying specific factory buildings while leaving adjacent structures standing. Japanese air defense commanders, schooled in the limitations of conventional bomb sites and the protective value of darkness and weather, could not explain this capability. Some attributed it to luck, others to superior American pilot training, but a few suspected the truth. The Americans possessed a technology that Japanese science had not yet mastered. The capture of an intact B-29 had been the highest intelligence priority for Japanese forces since the bomber's introduction. Previous crashes had yielded only wreckage, aircraft that had augured into the ground at high speed or been consumed by fire. But 42-24620, damaged by flak over Tokyo and unable to reach its base in the Marianas, had made what its crew hoped would be a controlled crash landing on the coast. The landing had gone wrong, killing most of the crew on impact, but the aircraft's nose section, containing its bombing and navigation systems, had remained largely intact. Japanese recovery teams had descended on the site within hours, cordoning off the area and beginning the delicate process of extracting the most valuable intelligence prize yet captured from American forces. Captain Tanaka had built his reputation developing radar warning systems for Japanese night fighters, working with equipment that was primitive by American standards, but represented the cutting edge of Japanese technology. He understood the theory of radio detection and ranging, had studied captured British radar sets from Singapore and American SCR-268 anti-aircraft radars from the Philippines. But when he began his examination of the B-29's radar system, he encountered something that transcended his technical framework entirely. The AN/APQ-13 was not simply a more advanced version of radars he knew. It was a different order of technology, built around principles and engineering solutions that Japanese industry could not have produced even if provided with complete blueprints. The first shock came when Tanaka opened the radar's receiver unit and discovered not the fragile glass vacuum tubes he expected, but sturdy metal tubes of a design he had never encountered. These were American subminiature tubes, mass-produced with a precision and reliability Japanese manufacturers could not match. The entire radar system employed over 200 tubes, each operating with tolerances measured in thousandths of an inch, manufactured in quantities that suggested American industry viewed such precision as routine rather than exceptional. Tanaka had worked with Japanese radar tubes that required constant adjustment, that burned out frequently, that varied in performance from unit to unit. The American tubes in his hands were standardized to a degree that seemed almost wasteful, as if the Americans possessed such abundance of manufacturing capacity that they could afford to make every component perfect. But the tubes were merely the beginning. As Tanaka and his team systematically dismantled and documented the radar system, they uncovered layer after layer of sophisticated engineering. The transmitter employed a magnetron that generated microwave frequencies with a power and stability Japanese equipment could not approach. The antenna system, housed in the B-29’s distinctive chin radome, could rotate to scan the ground below while maintaining precise azimuth control. The display scope presented returns with a clarity and definition that allowed bombardiers to distinguish individual buildings in a target area from 30,000 feet altitude. Each component reflected not just advanced design, but manufacturing capabilities that existed nowhere in Japan. The symbolic object that came to represent this technological disparity was not the radar system itself, but something far more mundane: the system's instruction manual. Tanaka had expected a technical document similar to Japanese military manuals, sparse, assuming deep prior knowledge, written for expert operators. Instead, he found a thick, spiral-bound book with hundreds of pages of detailed explanations, illustrated with professional diagrams, photographs, and step-by-step troubleshooting procedures. The manual assumed the operator might be a young man with only basic technical training, and it provided enough information to allow such a person to operate and perform field maintenance on one of the most sophisticated electronic systems in existence. Sections covered basic theory, component identification, common malfunctions, and detailed repair procedures. There were multiple redundant explanations, clear illustrations from various angles, and even a section on safety procedures that emphasized protecting the operator rather than just protecting the equipment. This manual, translated page by painstaking page by Tanaka's team, revealed something more troubling than mere technical superiority. It demonstrated an approach to military technology fundamentally different from Japan's. The Japanese military, operating under severe resource constraints and with a limited pool of technically trained personnel, concentrated advanced equipment in the hands of specialists. A Japanese radar operator received months of intensive training and was expected to become intimately familiar with every aspect of his equipment through experience and expert instruction. The manual for a comparable Japanese system, if one existed, would be brief, technical, written for men already possessing substantial knowledge. The American manual, by contrast, reflected a military system that assumed it would need to train thousands of operators quickly, that equipment would be distributed widely rather than concentrated, that average men could be taught to use extraordinary technology. This was possible only in a nation with such industrial capacity that it could produce sophisticated equipment in massive quantities, and with such educational infrastructure that average recruits possessed enough basic technical literacy to learn complex systems. The manual itself was a symbol of American abundance, not just of material resources, but of human capital, of an education system that produced men capable of mastering advanced technology, of an industrial system that could afford to make equipment reliable and maintainable enough for those men to operate effectively. Lieutenant Kenji Yamamoto, a junior engineer on Tanaka's team who had studied electrical engineering at Tokyo Imperial University, spent 3 weeks attempting to reverse engineer the radar's signal processing circuits. His conclusion, delivered in a report that would circulate through Japanese military technical bureaus, was devastating in its honesty. The American radar employs circuit designs that are theoretically elegant and practically sophisticated beyond our current manufacturing capabilities. More significantly, the quality and consistency of component manufacture suggests production facilities operating at scales we cannot match. Each resistor, each capacitor, each wire and solder joint reflects manufacturing standards we achieve only in laboratory prototypes, yet the Americans deploy this quality in operational equipment. This suggests not merely technical knowledge we lack, but industrial processes we cannot replicate. The radar system's most remarkable capability emerged when Tanaka's team finally managed to power the unit and calibrate its display. Working from the captured manual, and after numerous failures, they succeeded in generating a radar image of the surrounding area. What appeared on the scope was not the crude, difficult-to-interpret returns of Japanese radar, but a clear, almost photographic image showing the outline of hangars, runways, nearby roads, and even individual large vehicles. Buildings appeared as distinct rectangular shapes. The coastline was rendered with remarkable definition. An experienced operator, Tanaka realized, could navigate by this display, could identify specific targets, could guide a bomber to a precise aim point without ever seeing the ground visually. Weather, darkness, smoke, none of these mattered. The bomber crew could see through them all, guided by electromagnetic eyes that the Japanese had called the eyes of God. This capability had profound implications for air defense. Japanese tactics relied heavily on weather and darkness to protect strategic targets. Industrial facilities produced smoke screens when raids were expected. Fighters attempted to force bombers off course, so visual bomb runs would be impassable. None of these measures had any effect against radar bombing. The Americans could strike anywhere, anytime, under any conditions. Japanese air defense commanders, when briefed on the radar's capabilities, understood immediately that their entire defensive strategy had been rendered obsolete. You cannot hide from an enemy who can see through all concealment. But perhaps more psychologically devastating than the radar's capabilities was the evidence of how the Americans regarded this extraordinary technology. The B-29 that had crashed near Yokohama was one of hundreds in operation. Each carried this sophisticated radar system as standard equipment. The manual's matter-of-fact tone, its assumption that any reasonably trained operator could master the system, suggested that the Americans did not consider this godlike capability exceptional. They had industrialized the extraordinary, made the miraculous routine. Japanese engineers, struggling to produce even basic radar systems in limited quantities, found themselves confronting evidence of an industrial civilization operating at scales they had not imagined possible. Major Takeshi Kobayashi, chief of the Japanese Army's radar development program, visited Tanaka's facility in December 1944 to examine the captured system personally. He spent 2 days studying the equipment, reading translated sections of the manual, and questioning the engineers. His official report to military headquarters concluded with an assessment that bordered on despair. The gap between American and Japanese radar technology is not a matter of years, but of fundamental industrial and scientific infrastructure. We lack not merely the knowledge to build such systems, but the manufacturing base to produce components at the required quality and scale. Our universities produce too few engineers. Our factories lack precision machinery. Our supply chains cannot deliver materials of necessary purity and consistency. Even if provided with complete plans, Japanese industry could not produce this radar system in meaningful quantities. The Americans are fighting a different kind of war, one where industrial capacity matters more than warrior spirit. This realization, that spiritual strength and tactical skill could not compensate for technological inferiority of this magnitude, represented a profound crisis for Japanese military culture. Since the Meiji era, Japanese military theorists had emphasized spiritual factors over material ones. Bushido tradition taught that will and courage could overcome mere material disadvantages. The early war victories had seemed to validate this philosophy. Japanese forces, though often outnumbered and outgunned, had defeated Western colonial armies through superior morale, better training, and more aggressive tactics. But radar technology, and the broader industrial system it represented, could not be defeated through morale or aggression. You could not shoot down a bomber you could not find. You could not defend a target the enemy could strike with precision through any weather. Material reality had trumped spiritual strength in the most definitive way possible. Tanaka's team attempted to build a copy of the American radar, using the captured system as a template. The project failed comprehensively. Japanese vacuum tube manufacturers could not produce tubes meeting the required specifications in meaningful quantities. The magnetron design required materials and precision machining beyond Japanese capabilities. The antenna control mechanisms demanded bearings and motors Japanese industry could not supply. After 3 months of effort, Tanaka's team had produced a crude approximation that generated returns far inferior to the American original and broke down after hours of operation. The attempt had demonstrated, more clearly than any report, the industrial gap between the nations. What made this technological disparity particularly bitter was the realization that Japanese engineers understood the principles involved. They could read the American designs and comprehend the theory. They recognized the elegance of the solutions. They simply lacked the industrial infrastructure to implement them. It was as if a medieval craftsman had been given blueprints for a modern automobile. He could understand what each part did, could appreciate the design, but possessed neither the tools nor the manufacturing knowledge to actually build it. Japanese engineers found themselves in the position of that craftsman, able to study and admire American technology, but unable to replicate it. The eyes of God metaphor, which appeared repeatedly in Japanese technical reports and officer communications about the B-29’s radar, reflected more than just recognition of technological sophistication. It represented a theological understanding of the American advantage. In Shinto and Buddhist traditions, the ability to see all things clearly, to perceive truth through obscuring illusions, was an attribute of divinity. The radar system, granting this divine perception to ordinary American airmen, suggested that the Americans commanded powers that transcended normal human capability. Some Japanese officers, particularly those of more traditional backgrounds, interpreted American technological superiority in quasi-mystical terms, as evidence that heaven had withdrawn its favor from Japan. But others, including Tanaka and his engineering team, drew more pragmatic and more troubling conclusions. The radar system represented not divine favor, but the fruit of a completely different approach to organizing society and industry. The Americans had built vast educational systems that produced engineers and technicians by the thousands. They had constructed massive industrial complexes capable of precision manufacturing at scales Japan could not approach. They had developed scientific research infrastructure that supported continuous innovation. They treated technological advancement as a systematic process rather than the work of isolated genius. Most fundamentally, they possessed an economic system wealthy enough to invest enormous resources in developing and deploying advanced military technology. The instruction manual, which Tanaka kept on his desk throughout the war and preserved afterward, symbolized this systemic American advantage more effectively than the radar itself. Each page, with its clear explanations and detailed illustrations, represented an investment in making technology accessible to ordinary men. The Americans could afford to do this because they possessed such abundance of skilled manpower that they could train thousands of radar operators. They could deploy sophisticated equipment widely because their factories produced it in such quantities. They could write comprehensive manuals because they maintained technical writing staffs devoted to this purpose. Every aspect of the manual reflected a depth of resources that Japan simply did not possess. As American B-29 raids intensified through late 1944 and into 1945, Japanese air defense forces struggled against enemies they could barely detect and could not effectively engage. Night raids, conducted at altitudes beyond the ceiling of most Japanese fighters, struck targets with precision that weather and darkness did nothing to diminish. Japanese commanders, knowing their enemies possessed the eyes of God, understood the futility of their defensive efforts but continued fighting because honor and duty demanded resistance even without hope of victory. Pilots flew night missions against bomber streams they had minimal chance of intercepting. Anti-aircraft batteries fired at targets they could barely track. The entire defensive effort had become a form of ritual combat, gestures of resistance against an enemy who could see clearly while Japanese defenders fought in darkness. Private Yuki Matsumoto, a searchlight operator in Tokyo's air defense system, kept a diary through the final months of the war. His entries from March 1945, after the devastating firebombing raids, reflected the psychological impact of facing an enemy with such overwhelming technological advantage. We sweep the sky with our lights, hoping to catch the bombers in our beams so the guns can fire. But they come through clouds we cannot penetrate, drop their bombs with precision we cannot understand, and depart before we can organize effective response. We are told to fight with spirit and determination. But how does one fight an enemy who can see in darkness, who strikes from altitudes we cannot reach, who possesses tools we cannot match? We do our duty. We remain at our posts, but we know we are fighting forces we cannot defeat. This sense of technological helplessness extended beyond military operators to civilians experiencing the raids. Japanese civil defense doctrine had emphasized that proper precautions and communal solidarity could protect against air raids. But when B-29's began striking targets with precision through any weather, when specific factory buildings were destroyed while adjacent structures stood intact, when entire districts burned in firestorms that followed methodically planned patterns, civilians understood they faced an enemy with powers beyond their comprehension. The American ability to see and strike targets under any conditions seemed almost supernatural, not technology but sorcery. By early 1945, Tanaka's research facility had been reassigned from attempting to copy American radar to studying how to jam or deceive it. This effort proved equally futile. The captured radar operated on frequencies and employed signal processing techniques that Japanese transmitters could not effectively interfere with. Attempts to generate false returns failed because the radar's discrimination capabilities were far beyond what Japanese engineers had anticipated. Metallic chaff, similar to what the Allies called window, had some effect but required quantities of aluminum foil Japan could not spare. Every countermeasure avenue led to the same conclusion. Japan lacked the technical and industrial capacity to contest American technological superiority. The psychological impact on Japanese technical personnel was profound. Men like Tanaka, who had devoted careers to developing military technology, found themselves confronting evidence that their nation was simply outmatched at the most fundamental level. This was not a matter of catching up or of isolated breakthroughs that might restore parity. The gap was systemic, rooted in differences of industrial scale and scientific infrastructure that would take decades to address even under the most favorable circumstances. And circumstances were far from favorable. Japan was losing the war, its cities burning, its industrial capacity degrading under sustained bombing, its pool of skilled workers depleting through conscription and casualties. Captain Tanaka's final report on the B-29 radar system, submitted to military headquarters in May 1945, concluded with a section that represented more than technical assessment. It was an epitaph for Japanese militarism's fundamental assumptions. The American radar represents not merely superior technology, but a superior system for developing and deploying technology. They possess advantages we cannot overcome through willpower or tactical skill. They can produce in a month what takes us a year. They can deploy as standard equipment what we struggle to build as prototypes. They train ordinary men to operate systems that require our most skilled technicians. This is not a gap in technology alone, but in the entire industrial and educational infrastructure that supports technology. We have been fighting an enemy whose advantages we did not understand and cannot match. This assessment, though classified, circulated through Japanese technical and military circles in the war's final months. It contributed to a growing recognition among more pragmatic officers and officials that the war was not merely being lost, but had perhaps been unwinnable from the beginning. The material factors, industrial capacity, technological sophistication, resource availability, had always favored the Americans so heavily that Japanese spiritual strength and tactical skill had never represented realistic paths to victory. The radar system, with its godlike vision and its symbol of systemic American advantage, crystallized this bitter understanding. When Tanaka surrendered to American occupation forces in August 1945, he still possessed the captured radar manual, hidden among his personal papers. American technical intelligence officers, discovering it during a routine search, were puzzled why a Japanese engineer had preserved a manual for equipment he could not use. Tanaka, in fluent English learned during graduate study at MIT before the war, explained that the manual had taught him more about America than any other document. It showed him a nation that invested enormous resources in making the sophisticated accessible, that assumed its citizens could master complex technology, that built systems designed for mass production and wide deployment. It represented everything Japanese military culture had misunderstood about American society. The American officers, perhaps bemused by this philosophical interpretation of a technical manual, offered to let Tanaka keep it as a souvenir. He declined. The manual, he said, represented a past he wished to leave behind, a reminder of the years he had spent developing technology for an aggressive war, of the realization that his nation's military adventure had been built on profound miscalculations about enemy capabilities, of the psychological burden of understanding his side was technologically outmatched, yet being unable to change that reality. Better to surrender it to the Americans, to let them file it away in their archives, than to carry that weight into whatever future post-war Japan might build. But Tanaka did request permission to examine the latest American radar systems during the occupation. He wanted to understand how the technology had evolved in the final year of war, what improvements had been made, how the gap between American and Japanese capabilities had continued to widen even as Japan fought for survival. American technical officers, recognizing both his expertise and his intellectual curiosity, granted the request. What Tanaka saw in 1946, the radar systems on American ships and aircraft occupying Japan, confirmed what he had suspected. American radar technology had continued advancing rapidly even as Japanese capabilities stagnated. The gap had not merely persisted, it had grown. By war's end, the Americans possessed radar systems even more sophisticated than the one he had studied, systems that would have seemed like magic to the technicians who had examined the crashed B-29 in late 1944. This continued advancement, achieved while fighting a global war on multiple fronts, demonstrated something Tanaka had come to understand through his study of the captured radar. American technological superiority was not accidental or temporary, but the inevitable output of a system organized to generate continuous innovation. The Americans possessed not merely better